Hello guys. Today we are going to discuss about day 11 of the training in the FPGA development. Since so far we have developed on the hardware architecture using Vivado EDA tools, and then we have developed some projects like AND gate, OR gate, and also we have used IP integrator module from the EDA Xilinx Vivado. Then after we got introduced to the Verilog HDL, how this Verilog HDL structure will be there, and we made best use of EDA online tools as well. So that was being discussed yesterday's class, and I hope I will link that as well. So in this day 11 of the training, we will be going to the design flow again. What is the VLSI design flow? And every one of you should understand what is the design flow of FPGA and what is the design flow of ASIC design as well. So ASIC chips and FPGA chips are both chips are available in the market, but there is a huge demand in ASIC chips that we will get to know from this training today. And let us go to the today's agenda. What is today's to do? So we will be understanding Verilog HDL structure again. So understanding of FPGA and ASIC design flow. We'll discuss about FPGA versus ASIC chips, how they are made. I will share some of my experiences in the industry as well. And we will discuss about the Verilog HDL structure for a multiplexer example. So let us take 2 by 1 multiplexer and let us discuss how to write Verilog HDL based on different types of models in gate level model, in behavioral model, and data flow model. So yeah, let us start the class. Coming to the ASIC design flow or FPGA design flow, we call it as VLSI design because we are utilizing lakhs of transistors, or we are developing a complex design structure into a small integrated chip. That's nothing but very large scale integration. And this comes from the specifications. It starts from the specifications, as I have explained yesterday. So it will be like specifications that you need to acquire from the market or from the client requirement. And if you are working for any project, so that project building that chip has some specifications to be built on. So in terms of application base, if you are using this chip in the communication, or if you are using this chip in the robotics, or if you are using this chip in the industrial automation, so that chip needs to go through some set of specifications, because in communications, if it is working normally at normal speeds, and when it is triggered, if it applies in that way, that is okay. But in communications, in satellite communications or in the robotic automations, it should work with a good processing speed and good temperature resistance or any other physical constraints. And it should also have some good power optimization. It should consume only less power, and we need these type of specifications. Those are nothing but specifications from the vendors. So from the different set of clients or customers, we collect the specifications and we design. For example, take an example of Intel i7 processor or Qualcomm Snapdragon 888 processor. We can talk about how many cores it has, and what is the processing speed, and what is the temperature of operation, and what is the power consumption. I mean, and also what is the battery that has to be attached, whether it might be a 4500 milliamps battery, or you can take 5000 milliamps battery as well. So it depends on what type of components you attach, and whether this Qualcomm Snapdragon 888 processor connects with Ethernet Wi-Fi 6 or Wi-Fi 5, or is it compatible for the next generations of 5G connections or mobile hotspots, and what is the power consumption, how much amount of the battery is consumed by the processor for applications running in the background on a mobile for a day. So you need to discuss and you need to check on these kind of elements. So the major thing you need to focus is specifications first, and from that specifications you can set aside some of the architectural things that are available for a chip design, collect those chips, and then you can write, okay, now we will be writing RTL design and analysis. At this stage, we are writing Verilog HTL or VHDL codes. The RTL is nothing but registered transfer level language. What are all the elements in the architecture are nothing but registers that you design. Group of logic gates and group of transistors make a logic gate, and group of logic gates can make a register, and group of registers are utilized for bus data bus transmission or operations in ALU, or using controller counters, or connecting to the external and internal peripherals, so communicating with the IO ports. So all these kind of operations can be done inside a chip. So chip is the major central processing unit that can be used to do set of tasks on the motherboard or any PCB board. So some of you have asked what is a chip and why do we need a chip? And that chip is nothing but central processing unit where it does the multiple tasks by utilizing the outer peripherals. For example, if you take a chip and that chip you have developed using RTL design, RTL code, like RTL code is nothing but Verilog HTL code, and that Verilog HTL code made a chip architecture, and now this chip is using USB port to read the data, or this chip is using LEDs to turn on the light on the motherboard, or this chip is responsible for working of entire laptop and our mobiles. So how do we give this functionality? It's just simple. It has come from the RTL analysis. Now, after design and analysis of an RTL code, now your Verilog HTL is ready. What we do with Verilog HTL? We check the functional simulation. How do we check the functional simulation? By integrating some of the external codes, like external components. Let us think about, we have RTL code, Verilog HTL code, and for that we need to check the verification. So how do we achieve that functional simulation? By using test bench codes. So test bench are very much required in this entire design flow, because you, whatever script you have written in the HDL language, that needs to be tested on a simulation platform. So EDA tools have a simulation platform, and in that simulation platform you will be getting this test bench attached to the primary code, primary source file or primary RTL file, and then test bench verifies the input and output processing, how this code is working. So you have already seen that test bench working and all. So that waveforms and timing simulation diagrams and charts, that windows, all these things are nothing but simulation steps. And then we go for synthesis. This is the major step where whatever text file you have written in the RTL design, right? In the RTL design, you have text file, and that text file functionality is checked using this functional simulation. After you do all these things, scripting work is done, and then you need to assign some libraries. Like I have told yesterday as well, I am repeating this, what to add as a logic gate and which OR gate technology you need to use, whether it might be 3.3 volts or 5 volts, or what type of flip-flops you need to use, what are the lookup tables that should be enabled. So you have every element in a block. So whether you use that block, you should enable that. And that type of enabling and assigning the latest technology that you are looking for in the design is made from the synthesis. Hence, the script you have written will be understood at the gate level. Which gates to be used or which logic cells to be used will be taken from the gate level, and those will be attached to the FPGA or any chip that we design. So after synthesis, we get the gate level netlist. Then now there are two flows. One is FPGA flow and another one is ASIC flow. Till here, Verilog HDL is common for both of them. But both of them means it is a common step. Whether if you are designing FPGA flow, come from this flow, or if you are designing ASIC, design from the start in terms of ASIC. I'll explain, guys. So yeah. So now in the FPGA flow, the next step is implementation. This implementation will be done using the gate level netlist. Means we implement. Actually, we design. Design is major steps are placing of the logic blocks. at this near to the port or center of the port, and clock can be sitting in the center of the design for easily connecting with all the logic cells, and output ports communicating some of the blocks or registers near the output port. So that automation will be done using the EDA automation tool. Implementation is done. So placement and routing are the major steps in implementation. After routing, we go to the checking again. The verification will be done again. You can see the implemented design and also check the simulation part. You can run simulation again, then you can get the output. If that is not working, actually we have discussed on the day 9 of this training, you can see the actual FPGA design flow, where if you find any errors, you should come back to the specifications and you should be starting from this thing. Or if you got some errors at functional simulation, you can come back to the functional simulation and check it again, and then start doing implementation. Like run synthesis and run implementation, you need to run on the EDA tools. In the starting lectures, you can see how do we have done run synthesis and run implementation, and then we can generate the bit stream. This is the ultimate file that can be communicated for the hardware, and for that bit stream you can take this file and you can upload it to the FPGA. So that's how we are designing the FPGA program, FPGA chip and the program. So you take an FPGA which is ideal and which has no architecture on it. It was pre-built, means you have some 1 lakh logic cells, but after you write code for using only 50,000 of logic cells, okay, now 50,000 logic cells are get connected, and that has been utilized for some particular architecture like counter, memory block, multiplexer. You can turn this FPGA chip into some other device based on the program that you write. So another 50,000 logic cells, those are kept aside. You can utilize them after a few years, or after immediately you can rewrite the program by resetting the FPGA from the beginning. So that is the flexibility of FPGA development. Now come back to the same ASIC design flow. What we are going to discuss is after synthesis, we'll go to the ASIC flow, and then in the ASIC flow we can see two major steps: DFT ingestion and DV and STA. These are the major roles. Like DFT ingestion is nothing but we will be seeing some scan flops that are to be attached on the design for additional verification purposes, and and the physical constraint backgrounds. And then design verification is going through the protocols, UART protocols. All these verification things or simulation can be done using DV, design verification roles. Those engineers work. So here in ASIC design flow, every step you take DFT, DV, and then STA. These are all the individual departments where your design will be going in a flow from each department, each step, and to the all other steps. And then you can see uh, there comes the backend. This can be a front end, and then there comes the backend. Until here it is front end. So from specifications, RTL, synthesis, DFT, DV, and STA, all these are front end. Those are the front end engineer roles. Each one has a engineer role. And coming to the backend, this is the physical design. What do you mean by physical design? I'll show you an image in the next lecture. But in the physical design, whatever you have written in the functional scripts, logic verification or Verilog HDL scripts, those can be taken into the consideration, and then you can develop the entire physically ready-made, ready chip that can be that design can be sent through the manufacturing. So before manufacturing, the manufacturing machineries or industries like TSMC or Global Foundry, they need a design like some floor plan. Some floor plan is nothing but where these memory cells to be set up, or they where these block level designs should be set up. That is again a physical design flow. We will go through each step in a detailed way. If I find any time, I'll be giving you a brief example of physical design flow. as I'm working in the industry, I would be very helpful to drive you through the physical design flow. It will be very interesting. And after you design physical design, design your chip in the physical design environment, what you will be seeing, floor planning. You will place the cells. You will have a blueprint of floor plan, like in the house. If you can see, okay, dining room should be here, and you can see the puja room, or you can see the kitchen, or you can see the balcony. Wherever you see some analogy here in this physical design, in the same way we will be setting aside, okay, port should be on the external side, on the top left or right in the block. So also you can see some memory blocks should be here, and clock cells can be sitting in the center of them. So it will be based on the specifications. It will be based on the block level and full chip level. There are two levels. It is bit complicated, guys. I'll explain in the detail with an example if there is any extra class. And floor planning, then comes placement and route. Again, after placement and route, this is a step which is very much similar to the implementation on the FPGA. So, but here we are developing FPGA chip, and here we are developing ASIC chip. So please understand, guys. So placement and CTS and route. CTS is nothing but clock tree synthesis. Whatever clock you have written, those clocks are generated and connected through the different logic cells that are attached. So now the physical appearance is happening. Think of two things, guys. Whatever you have written on the paper, that should be available in the physical environment. If I write, okay, embedded C program in a paper, that should be implemented in a microcontroller like Arduino or Raspberry Pi. So physical appearance of the hardware, or physical connections, or physical functionality should also be related to the logical functionality or the script functionality on the HDL file. So in the front end, they work on the simulation environment, mostly in the virtual backgrounds. But in terms of hardware, they think the constraints and check the verifications. But in the backend, in this physical design, that is the major step where you bring the life to the script into the physical environment, and which this physical environment will be sent to the manufacturers. So after placement of the cells in here and there, and attaching clock to the sequential cells, to the sequential logic cells, and making the routing is nothing but connecting between the logic cells with the internal wires. As I have also already repeated, routing is the major part in the implementation, and placement is the major part. And now after place and route, we call it as place and route engineering. Then we optimize is nothing but whatever the wrongs or errors or mistakes happening in the design, that will be optimized. So after optimization, we will go to the DRC clean or LVS clean. This is a physical verification environment. So physical verification means, okay, these cells are utilized in a wrong way, or these cells cause maximum delay, or these cells are not connected. There are some loose pins, or some of the cells are overlapped in the application. So all this is done in the physical verification step of the entire chip design. So by using the help of EDA, so every step has one type of particular EDA tools. For example, in the floor planning, place and route, we have ICC2 by Synopsys, which is the leading company of EDA vendors. And then optimization can also be done in the ICC2. But in the LVS and DRC clean, we use IC validator. So that is another tool. And in the synthesis, we use DC compiler for ASIC design flow. But in the FPGA design flow, we have Xilinx Vivado, which we have used in the previous classes. So this entire flow is done in one single EDA tool. But in the ASIC, right, each step is very much complex, such that each step needs a single dedicated library oriented compilers, or the EDA tools that we are looking for. So after these things, we require each functionality. And some of the EDA tools will also have graphic user interface, where you can design them by opening the GUI windows. GUI window is nothing but you are seeing timing simulation waveform, right? That is an example of graphic user interface. Interface is a window. Interface is a window. In this window, if you can see some timing charts, and if you can see some hexadecimal codes written in this form. So this type of simulation window is provided by using graphic user interface. Some EDA tools have that. Most of the EDA tools will also have that. You have to invoke the graphic user interface. One command in the TCL scripting is start underscore GUI gives the GUI window. So after we make the design possible in the ASIC design flow through this all steps, you can make this chip ready for bulk production. Like you can give it to the TSMC, where it is a leading manufacturing company in China. So chips are very short. These they are banned. I mean, entire globe. In the globe, TSMC has the lithography machines for developing the chips. But now we are fortunate enough that Vietnamese have that chip design companies, and also some global foundries. And now Intel is looking for their own manufacturings. And one example of chip shortages, we can see Ford company has shut down the operations in different countries because of the shortage of chip, as well as there are many applications in that way. So yeah, this is the entire VLSI design flow. Remember this as it is, guys. If you have any doubts, just ask me at any point of time. And now let us go to the next point, next topic. What is FPGA and what is ASIC? So major differences, I mean, major advantages, or some basic things you should know when we are talking about chip design or VLSI design in this training. FPGA chip has logical connections based circuit that is pre-programmable. As I said earlier, if you use 50,000 logic cells for counter design, and if you want to increase this counter and also attach some of the logic cells to the existing 50,000, and you can attach LCD display on the counter instead of LED, then yes, you can restructure the program again, and you can reset it and rewrite the program according to attachment of LCD. Then prototype versions, yes. What type of prototype versions we have? We work with prototype is nothing but an example project. If you can apply on this FPGA chip, okay, this is done in the sample program or sample functionality, then you can utilize it in a complex way as well. So we test it first as a prototype, as an example project, and then we can run several times, rewriting the program on multiple times. So then you can see ASIC as application specific. No, if you are taking a FPGA chip and if you apply it in communications, and you can take that chip and you can apply in robotics as well, in the two different domains or in the IoT domain. But if you take the ASIC chip, if you can apply that chip only in the laptop, those are designed only for laptops. You can't take a laptop chip and you can't use it for another purposes of robotics. I mean, we can attach some external peripherals and we can hardly use it, but there are certain limitations for working environment, and ASIC chips are made for only some sort of applications and permanent connections that are not reprogrammed. See, as I said, in the FPGA you can use group of logic cells and you can reset them, and you can use another group of logic cells. But in ASIC, every logic cell you implement in the design, you place in the design, and you route them with the connections, those are used in the particular way. You can't increase the count of the logic cells and you can't decrease the count of logic cells. So that's what ASIC chips are made only with the specific number of transistors or standard cells. So those are not reprogrammable. And yeah, ASIC chips for designing itself, by utilizing this many EDA tools here in every step, every step. It is very difficult to use these many tools, and each tool costs very high in the industry. That is the reason this kind of professional training will be done using some well-known companies. And that this FPGA is a open source kind of thing. You can develop, as we are developing since last 10 days. uh, we have used FPGA chips on our own environment, and it is very much affordable in implementation. If you have board, it costs around 1000 to 5000 or 7000 at last, at maximum. But in ASIC chips, if you want to purchase a chip, it starts from at least 12,000, and you need other hardware as well. So if you are building your custom PC, and if you are getting i7, now it is 11th generation, I think 13th generation of i7, and if you take that chip, and if you want to utilize that processor, right, you need a motherboard, you need external cooling system, or you need hard disk for memories, that to be SSD or NVMe versions. So technology is evolving, you can't utilize. But if you take FPGA board, that is it, you can utilize FPGA board as microcontroller as well. So that's how the flexibility is there. You need to understand these kind of uh, differences between FPGA chip and ASIC chip. Where if someone asks you in any other environment, you should be telling, okay, I know how to design FPGA chips, and I will be designing ASIC chips as well. So which one is cost effective in bulk production? No, cost effective is ASIC chips, because if you take 1 crore for one design, right? With this design, you can manufacture crores of chips. That's how world is working. So only 1 crore for design implementation. In the bulk manufacturing, ASIC chips, uh, those are made in a bulk, right? So hence the cost reduces when you manufacture any product in a bulk count. But see, for one chip, one FPGA itself, it costs around 7000, and if you want to make it bulk, oh no, 7000 into same quantity crore, 7000 crores. So FPGA chips are not produced in bulk, those are made eventually, and you can reprogram and redesign the FPGA for your own industrial applications. So yeah, it depends. If you can see, you and your friend might have the same chips running in your laptops with i7, or if you have AMD Ryzen or Radeon chips, those are same in the particular set of laptops. So that's how these ASIC chips are made in bulk with same architectures. Now moving on to the chip design. In this ASIC chip, what exactly you are doing? FPGA comes with a board, and this chip works with the specific peripherals or the ports that are connected. And each chip, you can see in the back end, each chip port inside the chip, it will be connected on the PCB design using external peripherals and wires. So this is the Mars AX3 board that we have developed in the earlier stage, and you can take uh, this ASIC design, and in this design, in this chip design, and in this design, what we are focusing is, we are focusing on the external ports inside cells, and these lines are nothing but wires. So this is how, in a nanometer scale, we connect them. I mean, we don't manually connect, we use the help of EDA tool, and the automation happens in that. So that is the complex chip design, and this is also complex, but it is only for fewer prototype purposes and prototype applications. But ASIC, yeah, it is like using these chips in different environments, in robotics, in IoT domains, or in hospital medical domains, all these things. And once you develop this ASIC chip, you can run the OS, and you can also run the set of programs to work on machine learning and artificial intelligence or data analytics kind of thing. So there are set of applications using this. So yeah, this is how it looks when you take the ASIC chip outside. And yeah, now going back to the Verilog HTL. Let us come back to the Verilog HTL. And let me introduce you to the different types of models in Verilog HDL, which has behavioral model, data flow model, and gate level model. In that, how do we design? We can design in three different stages of the entire Verilog HDL programming. You need to understand three different program levels are available now. As we go further in this training, we will be understanding how to write a different set of things in different ways. For example, if you take multiplexer now, you can have gate level or data flow model or behavioral model. What are these? Let us go to the design. And Welog HTL is implemented for design and testing purposes. Yes, nowadays system Verilog is also used in terms of ASIC chip design industry. As I told earlier, system Verilog is nothing but advanced level of syntax written in Verilog HDL thing. But system Verilog has OOP concepts that can be OOP concept, object oriented programming concepts. So that is a way advanced level for Verilog HDL. And coming to the for both the ASIC and FPGA board designs, Verilog program is must. I have repeated this point. And now let us go to the checking of behavioral model, data flow model, and gate level model. So what are these? Why do we need these three models for the Verilog HTL? So let us go to the first behavioral model. Behavioral model is nothing but uh, how does the cell or how does the logic that you want FPGA to be working should be working in a behavioral environment. What is the behavior out of it? So behavioral environment, take a thumb rule. It takes the examples from lookup tables. It takes the logic and functionality from the truth table or lookup tables. So lookup tables or truth tables, it works in this kind. Now I have considered an example of multiplexer. So for a multiplexer, you have two inputs. I mean, 2 by 1 multiplexer. Don't get confused, guys. 2 by 1 multiplexer. In this 2 by 1 multiplexer, you have one selection point and one output. So 2, 1. And if you have two uh, inputs and you have one selection listing, and yesterday or day before yesterday in the previous trainings, I have told this can be one input D0 and this can be another input D1, and this can be your single selection point. And how does this multiplexer works? And it comes with the data input from two different ports, and output is decided on the selection port. For example, if it is 0 here, this is 0, and if you have D0 as 0 and D1 as 0, and based on the selection 0, this is selected. This input D0 input is selected. And now we are talking about selection 0 again, and D0 is 0 again. The output follows the first input. Got it, guys? So this is followed here. Now let us take S is equal to S is equal to 1. Now selection is 1. So now selection is 1, and this selection 1 enables the multiplexer to select the data input flow from this to output. In the same way it has done for S is equal to 0, this one. So D1. So now what is selected? D1 is 0. So here it is 0 again. Now what is followed? This is followed as the output Y. So in the selection is the main criteria. Now again we keep S as 1. Based on the S input, based on the selection input, we take which input to be enabled and which data should be flown through that input port. So now 1, again the D1 has changed from 0 to 1. Now this 1 is followed here. So as you can see, this is followed in this way. We have achieved the output. So if you can see this output, it is very much similar to the OR gate, AND gate. So when you have both high, the output is high. If you have any one thing low, all the output is low. So remember about truth table, guys. When you are developing it, you will be better understood. So coming to the Verilog HTL, how to write Verilog HTL in the behavioral model. You can see, take an example of truth table. Now in the every time any Verilog HTL comes with the basic things that I have said in the part wise in the yesterday's lecture. So the first thing is, you can see you need to declare module. What we are doing, multiplexer to 1, and we need to declare input, data inputs, selection input, and one output. So as I have told, input are wires and D0, D1 and S, and outputs are registers, reg Y. So all the inputs are wires and outputs are registers. I will show some gate level model as well, but now we are purely developing this Verilog HTL from the truth table. So understand, guys, this is your first step. Second step is to write input and output, and third step is to begin the code with always at the rate of inputs, always at the rate of inputs, or always at the rate passage clock. So then fourth step is beginning the process. What is your process? Process is, if selection is equal to 1, output should follow D1, and else means here S is equal to 0. If else condition, I know every one of you have understood. So if S is equal to 1, if S means yes, S is equal to 1, S is enabled. So S is disabled with 0. S is enabled if 1, right? If 1, D1 should be followed. Remember this. And if 0, if S is 0, if disabled, D0, I mean first input is D0 should be taken. So that is the nomenclature, like we have mentioned D1 and D0 to better understand what is the selection depend on it. So else S is equal to 0, hence end the process and end the module. Now you have 4 steps, 4 parts. Understand in the same way. First one is writing the module name and declaring the input and output ports. Now second step is defining input and input wires and output registers. What are the inputs from here? You need to declare D0, D1 and S based on this input, and output, one output register. So you need to mention wire and register in this behavioral model. And then third step, write the Verilog HTL by continuity. This is another property in the Verilog HTL we have discussed, like always is the continuity of the code. Only when the inputs change, this program is executed. If the inputs are not changing, this program will not be executed. So begin the process, and this process is nothing but fourth step, and you can declare it as fifth as the end module. This end module is connected here. Likewise, this end is connected in the begin. So basic elements of Verilog HDL programming, I will explain how to write and how to make you familiarize with the Verilog HTL programming. But understand, from the truth table, we are writing the behavioral model in this way. So in the same way, we will be going to the next level of the model, how to develop Verilog HTL. In this data flow model, we basically develop Verilog HTL, this type of developing Verilog HTL through the Boolean equations. What are the Boolean equations? So it has some specific syntax as well. So this is the Boolean equation. So this is the Boolean equation for 2 by 1 multiplexer. So hence from this Boolean equation, to acquire this Boolean equation, we can write simple operation, mathematical operation here. So this is a basic equation that can be converted into Verilog HTL. So here it is simple. You declare module 1 I mean module multiplexer, declare input ports and output you declare, input you declare. This is the second step. And third step, what is the process? Every time you question what is the process that you need to write. Here the process is assigning D1, D0. If based on the based on the input, you can declare you can follow what is Y. So if S is 1, take the D1. If S is 0, take the D0. That's what this entire declaration is defined. Don't worry about how this operation has been written. This will be explained in detail how to write when we start writing Verilog HDL programs. So in the Boolean equation. So if you have Boolean equation for group of set of cells, then you can take this into an example and you can develop it later. The last model can be gate level model. In the gate level model, what you are going to develop is you will be looking at the logic gates, logic cells, what are the cells available, OR gate or XOR, NAND gate or any other things or not buffers, and what are the input wires and input ports and wires connected between the logic cells. All these can be understood with the logic circuit, digital circuit, and then you can make a Verilog HTL using it. So with the physical inputs and outputs according to the among gates. So gate level model, you can understand in the name itself, you can have an example. So for example, in the behavioral model, we are understanding the functionality through truth table, and in the data flow model, we are understanding the functionality of the circuits through Boolean equation. So Boolean equation, truth table, and what else we have now? Logic gates. By seeing the logic circuit, you can develop the gate level model. It will be very familiar to us as we have developed few bunch of codes. Now see how it is written. First, every time you need to write module, you need to declare this is the step 1, and step 2 mention about input and outputs as it is declared. And then when you are assigning the functions through logic gates, you this is the process begins. So this is the third major step that is required, where you need to mention AND gate, OR gate functionality, and what are the inputs in the AND gate and outputs of the OR gate. Here, while writing the functionality in AND and OR gates, right, you need to be so specific. You need to declare the output first. I'll write. You need to declare the output first and inputs here. Okay. So you need to declare inputs in this way. Got it, guys? I'll repeat it for you. First, we are making module name with output, input declared, output and inputs declared, but we are not missing out the wires. So this T2 is wire that we have assigned and T1 is another wire. And also here after every logic cell, after every logic cell, make a thumb rule to remember. After every logic cell, you can see there is a wire. So that is important. So now coming to the program structure in the gate level model, you declare name. That is common in all the models, all the data flow and behavioral models as well. So first you declare the module by module name, case sensitive, and output and inputs. So after declaring, the second step is mentioning the output and inputs. It is common across the models, data flow and gate level model. I'll compare in the last slide as well. So output and input D0, D1 and S, and wires. What are the wires? T1, T2 and S bar. Here you are getting some output, right? After a logic cell that can be connected to the another logic cell using wires. So only the ports are nothing but which has a single direction of the input in this way. But these wires are nothing but it's a two-way communication. In two-way communication means data flows from left to right, let us assume. But some cells are again connected to this, and you can derive something from this. So wires are declared in that way, where you can easily remember by mentioning them after logic cells. So again, step 2. These might be little confusing in the beginning, but if you start writing right, it will be easy for you. So declaring output, input and wires is the second step, and functionality. Again, it is a process. But in these three models, what we are changing? We are changing the process according to the data flow or gate level or behavioral models. So fourth step, end module. Which one is easy? Just let me know. So based on the logic circuit, understanding this logic circuit and connections and connectivity. Okay, now D0 and S bar should be multiplied. So D0 and S bar is multiplied, and the output is given in the T1. Now here it is D0 dot S bar, and here it is D1 dot S. I have written it very badly. So now it is written as D1 and S. Now what it is? D1 and S are added. These two are added now at the output of Y. So again, Y is nothing but D0 dot S bar plus D1 into S. If you can see this, you can see it is the Boolean equation. Nothing but D0 dot S bar, D1 dot S, D0 dot S bar, okay, dot S bar, and D1 dot S. So hence we are achieving the same functionality. The output will be the same with multiplexer in three different models, in behavioral model or in the data flow model or in the gate level model. It is same. The output is same. So why are we making these three different types of models? It is on the feasibility, or it is in the availability of the convenience. So you can see one single code here, which is written in the three different versions for 2x1 multiplexer. Take a screenshot of these guys. As I have explained, I thought it will be very helpful when you keep it here and you can understand. Don't worry about this truth table. It is same in the earlier versions. You can write it down and you can understand how this is, how these models will be working. Gate level model, you can see logic gates. Data flow model, you can see Boolean equation, data, Boolean. Behavioral model, behavior comes from the truth table. So make a hard and fast rule. So this is the day 11 of the training, and you can see that multiplexer is somewhere available in the architecture inside the chip, and now we are enabling it. We are utilizing it, and this entire FPGA chip will work as 2x1 multiplexer if we want. So that is helpful. So this is the end of the class, and if you have any questions, just let us know in the chat box, and you can talk to us all the time. You can chat with us in WhatsApp as well, and do follow us in the different platforms in the Instagram and in the YouTube as well. So thank you guys. See you all in the next lecture.